Hello, one. So we have another AMC 12 problem. So this was a number 19. So what we are given in a triangle ABC, side lengths are integers. So let's highlight this. And the cosine of the angle A, cosine of B, and the cosine of C is given. And what we want is the smallest perimeter of the triangle. Okay, so we are given only cosine values of each angle. So which is a good indicator. We might be using maybe like log cosine, but we have no size given. So that's what we are trying to kind of like find the least possible value of. So it might be still useful, but I'm gonna kind of try that as my last resort. So another thing I'm gonna try, like since we have a lot of like angle cosine values, so maybe we can just use log cosine instead. But to do so, we need to find their like sine values. So which is why I just want to remind the Pythagorean identity. So, you know, if you have the sine square of some angle plus cosine square of the same angle. So this is equal to 1. So you can prove this by unit circle or something else. This is the one of the most important identities that we have in our trig, right? So if I plug now into this, so if I want to find the sine value, so the sine square of theta is equal to 1 minus cosine square of theta. So in this case, I can just take the 11 over 16 for cosine of A. So from here, so I will say, actually, let me write this first. Cosine square of theta. You can even take the square root of both sides. The sine theta is equal to 1 minus cosine square of theta. That will be under square root. So based on this, like if I want to use each angle, so sine A is equal to 1 minus cosine, like square theta is cosine theta square. So which is why we can square cosine A, which is going to be 121. Or actually, I'll just write 11 square over 16 square. And then this is the under square root. So when you find a common denominator, so that will be 16 square minus 11 square, which will be like the difference of square. You can just square and subtract as well. But so 16 minus 11 is just 5, right? So that should be 5. And then 16 plus 11, 27. So I will just write as difference of square. And then that will be 16 square. So this is 9 times 3, so I can take that 3 outside, so that should be 3. And then 3 times 5 is like 15, so that should be root 15 over 4. So we know that like cosine value of A was a positive, which means A has to be smaller than 90 degrees, so the sine value of that as well, so which is why this has to be positive. So let's keep this in mind. Okay, so we have something at least. Actually, this was 16. So this is now 4. So this is divided by 16. And if you use the same thing with the other two, so you will get cosine, actually not cosine, the sine A means sine B is equal to root 15 over 8, which is you just like plug the 7 over 8 in this case. So 1 minus 7 squared over 8 squared. So 8 squared minus 7 squared. So the difference is like 1. And the sum is 15. So 8 will be denominator. And the last one is the sine C. But in this case, like cosine value is negative, which means the angle C has to be larger than 90 degrees because the sum is 180. So it can't be larger than 180. So it's going to be either less than 90 or larger. Might be equal to 90, but it's not. So in this case, so that means C has to be the obtuse angle. So, but if you take the sine value of that, the sine value of something in the second quadrant is positive. So, and if you plug it, so you will just root 15 over 4. Okay, so why this is important? Because as soon as we have the sine values, we can just apply our law of cosine. Just to remind, so the like law sine, actually, law sine was the sine value of one angle over that corresponding side is equal to sine value of another angle divided by corresponding side equals sine value of the third one divided by the side C. So this is law sine, right? So now we do have the sine values like root 15, root 15, root 15. So we just care about somehow like the ratio. So then I can just take the like root 15 and multiply all these sine values by root, because I can multiply by root 15, because if I just replace with those sine values, you will get this fraction in the numerator. So I can multiply, actually divide by root 15. So you will get this, such I think 3 over 16 over a, so which will be 3 over 16a equals, if I divide the root 15 over 8 by b, so I mean divide by root 15, so root 15 will cancel, so you get 1 over 8b, and then the same idea, so you will get 1 over 4c. So since all of them are like multiple of 4 in the denominator, so I can multiply the entire equation by 16, so you will get 3 over a is equal to 2 over b equals, if I multiply this by like 4, so the 4's will cancel, so you get 4 over c. Okay, so since we are trying to find the smallest value of the perimeter, so we can just say a is 3, b is 2, and c is 4. So if you add them, so you get smallest to be 9. So this is like one way we can just kind of get what we want. So I think using the law of sine was kind of reasonable to deal with, because we have this cosine values of each angle, so we can always convert to sine values of those by the identity, which I did. But this was this first approach. The second thing I can try is actually using some basic definition. So because we know that like the C value, angle C, is larger than 90. So I'm gonna make a triangle just to visually see. Okay, so let's say this is my triangle. And I'll take the this one C, this one A, and this one B. So as soon as I have this, like we now need to write the cosine values of each angle. So we just need a right triangle, which we do not have. But this telling us this is a obtuse angle, so we can extend this way and then make a right triangle. But when you do so, there is this right triangle, something we are going to get, will have only this side, so not the other two sides. Since we know that the angle C was over 90 degrees, so I can just drop the altitude from that to side AB, because if I do this, right? So then I have a right triangle right here, right here. So I can just relate every side. So let's use the given information. The cosine A, so the cosine value of this, 11 over 16. So if I say this is H, the cosine was the adjacent side divided by hypotenuse side, right? So that means 11. I'm going to call this is 11x, and this is going to be 16x, okay? And the cosine B is given, so which is 7 over 8. So whatever this segment, I'm going to call 7 y, and then the hypotenuse of B side, like angle B, will be 8 y. So now we have, this is altitude, so we can kind of use the Pythagorean right here and just relate x and y, because we just need x in terms of y, or the other way around. So if I use the Pythagorean, so this is h, right? The square of this is equal to square of this plus square of this, or you can just take this h squared alone. So that will be 16x squared minus 11x squared. This is going to be equal to h squared. So then I can just do the same thing with the other side. So 8y squared minus 7y squared. And this has to be equal to both h squared. So I can square and subtract, but I will take the difference of squares. So 16 minus 11 is 5. So that means 5x. And then 16 plus 11 is 27x. So this is the left side. 8 minus 1, like 8 minus 7 is 1. So that should be 1y. And then the sum will be 15y. So I can see it has 5, and then I can divide by 3, which is 9. So that will be 15. So it will cancel with that 15. On the left side, we have 9x squared equals y squared. So that means y actually equals 3x. Okay, this is good. So now we can make these one variable. So y value is 3x. So which means this has to be 21x and this has to be 24x. So we are trying to still find the possible smallest primitive, right? So we just need to add the sides. So now we have like the 16x is one side, and then this is 24x for BC. And then the AB is 21 plus this, which is 32x. So since we are trying to minimize the each side with integer segment, so we can see we can divide all of these by 8. So if I do that, so that will be 2x, like 3x, and 4x. Okay, so since we want to get the smallest, so I can choose x to be 1, so that will be 2, 3, and 4, so that is equal to 9 as well. So I think this is a bit better than the first approach because we never like use the law of cosine or law of sine. We're just using the Pythagorean, which is our like backbone, and also just the definition of the sine, cosine, whatever, okay, functions, okay? So that was my second approach. But there is also another way we can use, which is log cosine. At the beginning, I kind of said, since we have a lot of like cosine value of each angle, so maybe we can write the log cosine. So log cosine was telling us when you square one side, that is equal to sum of the square of the other two sides minus twice of these two sides. So that will be B and C times cosine value of the angle that is opposite to this side that is alone. So which is, I'm going to call that cosine A. And then same thing with the other one. So B squared equals C squared plus A squared minus 2 times like A times C times cosine B. And then if you do the same thing with this C, so that should be equal to A squared plus B squared minus 2 times A times B times cosine C value. So we can just plug these numbers. That will make these guys are gone. So we have 3 like variables. But when you try your best to like substitute something, for example, if I take the like B squared and plug it right here, and then take C squared, plug it right here. So you will get one equation in terms of like this side will be A squared, and then this side will be in terms of C and A. This side will be in terms of A and B. So it might help a bit, but I will kind of leave this approach for you to try because there is also another way to get this answer. So by using the log cosine. And I hope you can handle that. So, but otherwise, I just kind of go with other two approach. Okay, but this one has another solution as well. So I'll see you in the next video.